So, I'm here with Nina Kopacz, a postdoctoral researcher, is that correct? At the Utrecht University in the Netherlands, who does a lot of research inside earthbound caves in hopes of better understanding how we might look for life off world, particularly on Mars. Here at the conference, we're in the not the Canaries. That was the last conference. We're here in the Azores. I can't pronounce that. I think it's Azores or something like that in Portuguese. And we're on the island of Terceira at a conference on subsurface life, and organized by the European Astrobiology Institute. And so, Nina, just tell us when you go into a cave. You just finished your doctoral thesis, I believe. I read a chapter from part of that. Is that correct?
hmm
And when you go into caves, you're looking for blue-green speleothems. Is that how you pronounce it?
Yes, so we're looking at any speleothems really. So these are secondary cave minerals. So in lava tubes, they're the minerals that precipitate out after the lava tube has formed. So lava tube forms, that's just basalt, and then later on with the water rock interactions and also bacterial rock interactions, you get the precipitation of secondary cave minerals, and these are called speleothems. And some of these are blue-green, and those are ones I've been really interested in. They're copper-rich
Uh-huh.
speleothems, and we also find bacterial mats associated with these minerals. So the question for us is, are the bacteria playing an active role in precipitating out these speleothems, or do these speleothems form independently of the bacteria? That's sort of the goal of the research, is to find that out, because if the bacteria do play a role in aiding these speleothems to precipitate, then these could constitute a good biosignature, because that means that these form in the presence of life, uh,
So in
and
other
not
words,
just independently.
if we are using a robotic rover to go inside a lava cave or any sort of cave on Mars, if we can find one old enough that might have you know might have been formed during the time that Mars had liquid water. That's a
hmm
key, one of the keys. If we found the secondary signature,
hmm
that means that they might have this might be a biosignature of life, a secondary biosignature. Is that correct?
Yes, that's correct. That would be something to look for with the rover. That could be a sign of life.
And what would you consider as a a primary biosignature? If this is a secondary, is this
Well, I mean, the best way to find life is just to find the life, right? To observe the life itself. Of course, on Mars, that's difficult and probably will not happen for many reasons. First of all, because if there was any life on Mars, it's probably long gone. The life itself is probably extinct because the conditions on Mars are just not favorable for life anymore.
even
So,
underground?
even underground, probably, yeah.
Hmm.
So you would rather find a remnant of life, so like this, a mineral that was precipitated by life, or perhaps a microbial fossil, but not the life itself anymore.
And it's unlikely that we're going to find any microfossils on the surface due to what, radiation.
Yeah, radiation damage is definitely erasing a lot of the surface fossils, but yep, maybe even a little bit below the subsurface we can already find something. But
So now your talk mentioned your exploration of Iceland, caves in Iceland, and you mentioned that these were pretty uh, desolate caves. There's nothing, very little nutrients for these
mhm.
species of microbes. Why is that? And they were actually not very deep. The lava. Were these lava tubes or caves?
Yeah, so these are lava tube caves, I guess, lava tubes with entrances that we can access. So, um, but yeah, there's very little surface nutrients coming in. So there's very little organic carbon coming in from plants or from animals from the surface, because it's a lava desert up there. There's very few plants and animals. So the bacteria that live inside the caves, they can't rely on that organic carbon coming in. They can't rely on heterotrophy. They need to find their nutrients within the caves. And there's also no light in the caves, so they can't rely on autotrophy. They need to rely on chemolithotrophy. At least a fraction of these microbes. They need to first get their energy from the rocks, really. And then the organic carbon they produce, maybe other bacteria can feed off of that. But it's really an isolated, closed system that the primary producers there need to be using the energy sources within the cave.
Within the cave. And we have this on Earth as well, bacteria that uses the
Yeah, exactly. On Iceland, that's why it's such a good analog site, is because the mineralogy of these caves is similar to that of Mars, and there's very few energy sources.
So when is NASA actually going to start sending rovers into lava caves on Mars? Do you have any idea?
Well, I don't know. We have to start with the moon first, right? We're going to the moon, and there's already some mission proposals to go into caves on the moon, like the moon diver mission. So
Right.
hopefully something like that will be funded soon, and then Artemis will go to the moon. We'll build up the base there around the moon, and from there we'll go to Mars and hopefully go to a cave. I don't know, maybe in the 2040s, maybe in the 2050s. This all depends on a lot of things.
Okay.
Yeah.
Well, anyway, thank you so much for your time. It's all very fascinating. If you were putting odds on finding microfossils in a cave on Mars, would you care to venture a guess
As to
as to the odds of finding microfossils in a subterranean environment? Do you think it's a 50-50 chance?
I guess so, because we just don't know. We don't know how the origin of life happened on Earth, and we really don't know if it happened on Mars. So.
And what's fascinating, we still don't know the origin of life on Earth, right?
Yeah, it's still a mystery. But
Well, thank you so much.
thank you.